Welcome back to another episode of Adventures in Machine Learning. I'm one of your hosts, Michael Burke, and I do data science and data engineering at Databricks. And I'm joined by my co-host,
Ben Wilson.
Cool.
I do software stuff at Databricks.
That sounds fun.
It is. Really smart people I work with.
Yeah, so I've heard. So we're actually, just to give a little bit of insight into how these recordings work, when it's just panelists, just myself and Ben, we typically just shoot the shit for at least an hour and then realize that, we have to record this episode, and then quickly put together a plan. And that's what you're about to see today. So we've been talking about all of the illegal NDA-driven things that can't be discussed, all the super secrets. And instead of discussing those, we're going to be discussing science versus engineering. And specifically, if you're working in industry in a data profession, you might be coming from sort of two different backgrounds, typically. One is sort of an academic PhD, like researcher type of mindset. Another is more of the computer science implementation mindset. And then, of course, we'll have that catch-all category for everything that doesn't fit into that, such as myself. But these two roles and these two sort of mindsets are really, really valuable, but in different settings. So, Ben, to you, what is a scientist and what is an engineer?
I think the analogy that we were using before we started recording was me regaling you with history of my previous life before I got into data science and ML and software engineering. So I worked at a company that made LEDs. And because of the nature of what we were doing, we were attempting to innovate on designs. And that's not, hey, we bought some IP from some company and we're just manufacturing this thing. Those companies exist, but that's not where I worked. I worked at a place that was inventing the new technologies and coming up with new designs and building new structures that you're actually growing in these reactors. So we had two separate teams. One team, R&D, and the other team was process engineers. And when you break that down, that's science and engineering. Each of those teams had people with different backgrounds. So we did have people on the process side, the engineering side, that had doctorates that were, diploma carrying scientists that were applying their knowledge of advanced material science or chemical engineering into the production of LEDs at large volumes, so industrial manufacturing. And then we had people that came from an engineering background that worked on R&D. They were there to help scientists run these reactors so they could run their experiments and test things out. But both of those teams are working towards the same end goal, the ultimate goal of capitalism, which is make this company more money so you can dominate an industry and you can produce, better product. And there are other lofty goals, like we can reduce carbon emissions, throughout the world by making, light bulb replacements. Lofty goals that actually were met, which is kind of cool, thinking back on it. But aside from that end goal of profitability of the company and, enhancing shareholder value because it was a public company, that one goal is split up into two different, sort of topics when we're talking about the operation within the company. So you have the engineers that are focused on solving a problem. And that problem is, how do I make this widget, this LED structure, as efficient as possible while maintaining product quality and getting my yields up as high as possible? So you're focusing on operational excellence effectively. And there's a bunch of science involved. You have to understand, how are these things grown? And why do I have 1,600 knobs to turn here with every run that I put into this machine?
Yeah, it sort of sounds like optimization with a closed set of criteria.
Not as closed as you might think. It was pretty wide open.
Hmm.
uh, and you had to understand when you make a change on something, you change the temperature of the growth, like during a growth layer, or you change the gas flow rate, uh, like the volumetric flow rate, or you're changing mixture compositions between the different carrier, like the carrier gas and the actual active gas. You have to understand what the implications are for that. Like, are we cracking the triethyl off of this you know molecule that we actually want to land on the wafer surface at the right time, at the right physical place inside of the reactor chamber? And what does that do to the crystal lattice? And can we preserve, you know, an effective high quality crystal as it's growing? There's a lot of things you have to understand about material science and about chemistry and about physics. And you learn that stuff if you're an engineer like I was on the engineering side. But you're also focusing more on controlling that process. Like, hey, how do I get the light emitting from this thing to be within a target range? Trying to grow this thing to hit 450 nanometers, plus or minus 3 nanometers or something. Like, that's my target. Well, there's 17 different knobs that can affect that across 8 different layers. So you have to know your tooling, like how it behaves. You have to know the science and the theory behind what's going on. But then you're approaching each of your runs that you're executing, you're using the scientific process. You have a conjecture, formulate your hypothesis, you run your experiment, which in MOCVD land, every run is an experiment effectively, because so many things can change. The morphology inside the reactor changes. Nozzles get partially clogged. Heating elements age. There's loads of things that go into it. So you're fighting against variables and fighting against chaos in order to try to control something and make it consistent and reproducible. The other side of that house, the science side, they're not working on optimization hypotheses. They don't care, and they shouldn't care. It's not their realm of responsibility. What they're trying to figure out is what's that next structure that we need to build to meet our goals for the company. We need a brighter LED, or we need an LED of a different color, or hey, we're going to be introducing a new product line next year that's in a completely different spectrum range. So I remember them working on stuff like near UV LEDs, which was fascinating to me. And I remember sitting down with a couple of scientists that I knew. I was like, how are you guys going to make the structure in order to do that so we don't have like leakage loss of current? Like, do we have to dope it differently? Or I remember asking this one guy that I was good buddies with all these questions. And he just looks at me. He's like, I don't know, man. Like, we haven't even like worked on it yet. I was like, well, so you're doing like pure scientific method research here? And he's like, yeah, man. Like, we have some like hypotheses that we discuss amongst our group, and then we have to run 6 months of experiments to figure out which one of those is going to pay off. But he's like, the first 3 months is probably just going to be shipping dead wafers that are used for metrology only, because we have to invent something new here. Oh, that's cool. And then he would start asking me questions about like, hey, that structure that we made last year, I saw, a couple of your reactors are at like 98% yield. That's pretty cool. How'd you do that? And he starts asking questions to me about like, was it, do you focus on this thing, this part of the structure? I can't tell you what the structure is, but he starts asking me stuff about that. I was like, actually, no, that doesn't have any bearing on it. It's this component that makes it more successful. And we found this out through running experiments based on this to widen our process acceptability range, like the threshold of how much our process can deviate. And he was like, wow, that's fascinating. Like we never thought that that was an impact. And those sorts of conversations, the reason I'm telling you this story is we think about problems and we're approaching them from a completely different perspective. So we're both those groups were doing science. We're developing hypotheses, we're testing them, but our goals are completely different. So their goals are, build a manufacturable process and a, a new structure, recipe, template. And I'm in there fine tuning that template to eke out as much yield as possible while still producing product that is as good as it can get.
Okay, I think I'm following. Let me ask some questions. So, the core difference of how you would describe what an engineer or a scientist is tasked with doing is engineers are determining the best way to implement something, and scientists are trying to determine what's the next big thing. Is that sort of the high level?
I would say that applies to, like, in general, yeah. Uh, Science is about the undiscovered country,
Right.
figuring out something new, a discovery, an invention. And the way you go about that in a controlled manner is using the scientific method. But engineers, like, by virtue of their job title, usually, and like what they're tasked to do when they're employed at doing something, is to produce something
Right.
at, like, in an efficient manner. It's not to go and invent something new. That can happen if there's a problem that's presented, there is no solution, and you've exhaustively tested out available solutions to your problem that just don't function. Sometimes you are going into research mode and building a new invention to solve this problem. Nothing wrong with that. Nothing at all. But the reason we're talking about all of this in this in the realm of software engineering and development practices is a lot of people don't do that rigor when they're trying to solve a problem. They just immediately go into research mode. They're like, I'm smart. I can figure this out. I'll go and build a solution. And if you take that person, compare them with somebody who goes through the process of saying, is there prior art here? Is there something I can use that will make this solvable faster, more reliably, so I can move on to something else? That second person is going to solve this problem really quickly and then go do other things that are more useful.
Right. So let me explain how I think about the science versus engineering dichotomy. And I'll use your analogy of the undiscovered country because this was how it was explained to me for the first time back at my prior company called Tubi. So I had just built this super fancy tool. I spent a lot of time. It worked. It was tested, and it solved a real use case that was important. And my manager came to me and said, "Hey, great work. We're not going to use this because the company doesn't care about it anymore." And my little brain was like, "Well, damn, that's super sad. I worked so hard. This is my child. This is my baby. I've nurtured it into an amazing state, and now it's just going to be thrown into a dumpster." And I remember I was chatting with another data scientist about this. He was known as like the chill guy on our team. And I had seen this happen to his project several times, and he always took it in stride. He just, whenever his project was canned, he just said, "Hey, that's fine. I'll work on the next thing. Give me the next ticket." And so I wanted to understand how his brain worked and how he sort of could let go of his babies so easily. And what he told me was our job as data scientists, and it's more in the decision science realm, so informing decisions with data, our job is to create maps. We want to see what is out there, and then we present those maps for key stakeholders and key decision makers. And our job is to make the map as accurate as possible. And also, maybe if we discover some things like, oh, there's a berry bush over here, there's water over here, we should probably have some intuition about what is valuable to our overlords. But we're getting maps. And that was super, super transformative for me because it made me realize that the maps are sort of just a data point, and we can get a better data point or a worse data point, and all that matters is the information contained in there local to that time. So maybe within a week or two range. After that week or two range, your data point might not even be valid anymore. And so this process of building maps, I think, is one thing that is consistent between engineering and scientists, or sciencing, I guess. Uh, and Ben, I'd be curious your take. So you sort of describe science as this sort of open floor for curiosity, and we say, how are we going to make the company 10 times more money via this new innovation? And then conversely, engineering and sort of building is very focused, and we're looking to optimize a more concise and well defined set of problems. But I think both share this relationship of finding out what the unknown is and then acting upon it. And that's the process of sort of filling out a map. If you've ever played a video game where you explore and then you have a map and suddenly the map becomes green or blue with your terrain, it's the exact same analogy that I think of. So, what are your thoughts?
I kind of like that analogy, and I'm going to steal that. Um, so thinking about as you were just describing that, two things pop up to my mind immediately. One is the video game map exploration. The scientists would probably be the ones that would be figuring out what path we would be taking of like, hey, we want to go through this mountain pass because we understand that that's going to be probably more efficient to get to the other side to see what's over there. And they would also determine a direction. And that direction, like the end goal of where we want to get to, maybe that, it's probably management at a company that's doing that. C-suite is saying, here's where we need to get to. That continent is over there somewhere. We have no idea how to get there. But we would have scientists that would do the analysis of what are we estimating the terrain to be like at these different places, and what is the optimal vectors that we need to travel down in order to get there. The engineers are not involved in map making whatsoever. The engineers are the ones who are saying, a good engineer would say, what vehicles do we have at our disposal right now? And which ones match up with what the scientists are telling us the expected terrain will be like? Should we think about, you know, large vehicles that can get over, you know, any type of terrain but consume a lot of fuel, or smaller vehicles that need to skirt around difficult terrain but are very efficient with fuel so we can go further without having to stop or something? That's the engineer's role. The problem becomes when you have somebody who's in the engineering role who thinks that they're a scientist. So they approach the engineering problem like a scientist would, which is just trying to figure something out from, you know, with no context. So if we were saying, "Hey, we need to make a trip to this other side of where we think the map is. We don't know what's over there." An engineer who's got that thinking cap on of like, "I'm a genius and I can figure this out." They're going to disassemble all the vehicles that are sitting in the garage, and they're going to build something that's like, "Hey, it's amphibious, it's got big tires, and it's got freaking helicopter blades on the top, so we can go over everything." And then you start the journey and everything breaks, and the vehicle just, it's broken. Like you can't make your journey. That's a danger. Another danger is somebody who's excellent at cartography and understanding geology, one of those scientists. You tell them to drive the car on the road out there, and they like drive it straight into a rock or a tree or something, break the car. This was a perfectly functional vehicle that we were about to get in and use, that the engineers know how to use really well because that's their job, is to get to a location. Uh, and then somebody who doesn't know how to operate it breaks it. So yeah, I like that analogy. It's really good.
Yeah, thanks for running with it. But I just wanted to hone in on one point, which is, and it's a working theory. We can debunk this in the next 3 minutes potentially, but I would argue that it's a continuous scale of between science and engineering in terms of this map making concept. Like both share the goal of defining a map and then acting on the map. So with engineering, it's typically a much more closed space. You have three sets of vehicles that you can choose from. And all right, based on these six criteria of the current terrain, this vehicle is best, this vehicle is second best, this vehicle is third best. Cool. In science, though, you're still sort of doing that same thing, except just to take a data science analogy, your loss function is a bit broader. It's not optimizing to the terrain, it's optimizing to the scale of the innovation and sort of letting your curiosity drive that loss function and your intuition about what is valuable. So it sort of seems like it's all the same process, just with different amounts of specificity of the loss function. Does that make sense?
and and completely different skill sets.
Yeah, yeah, that's a good point.
So if you're working in a capacity as an engineer, your your goals and the tasks that you're determining what you need to do are completely removed from research. Like you're 100% right. Like research shouldn't have hard guardrails on how it's being conducted. You're going to stifle innovation if you do that. You need people to try a bunch of crazy stuff. Sometimes the crazy stuff is the stuff that ends up panning out. Where And that was the type of thing that I saw at that other company. A lot of times we would see sometimes like what the scientists were testing out on some of their reactors, and you look at the recipe and you're like, what the hell are they doing here? Like, there's no way this is going to work. And sometimes I would talk to people that I knew. It's like, what are you testing here? They're like, well, we need to know what the bounds are of like what happens with this combination of parameters so that we can know what the process bound is. They're like, oh, you're intentionally making junk. And they're like, yeah, we're expecting it to fail, and but we need to validate that it's going to fail where we think it's going to fail. Like, oh, so that's how we get our process controls for production. They're like, yeah, that's what we're doing. We're prepping this for production. So they test a bunch of stuff. It's not exhaustive. They don't have, infinite time and money and resources, but they would do a really good job of telling us like, hey, don't grow this layer too thick because this is what happens 99% of the time. And then if something goes wrong in the reactor in production and that layer grow like some hardware fails or something, and now gas is flowing in at an unrestricted rate during this growth layer, when we get the wafers out of the reactor, we look at them and then look at the data and we're like, oh yeah, R&D told us like this would happen. And now we know where to go in the tool to fix what went wrong because we know this mechanism and how this happened, or at least where to go and verify.
Right.
That's not too different from like software development as well, except in our world, setting job titles aside and stuff. You know how much I don't like the term data scientist.
I do.
Um, there are people that are working on pure research that are going to be used in industry by people with the job title data scientist. A lot of them are computer science PhDs. Most of them have job titles of software engineer, principal software engineer, distinguished software engineer, whatever, at a big tech company. And they're working on innovations for the next big thing. Or they're working on something that's total garbage, but they're going to learn a bunch along the way and realize this isn't really viable, but I know where to test next. And those innovations eventually make their way, if they're successful, into tools that everybody else uses. Like fundamental frameworks, stuff like TensorFlow, PyTorch,
Python.
transformers.
Mhm.
You have these tools that are written for people to use and build things with, but you don't need to go when you're presented with a problem that might seem unique and you don't know if there's a solution for it. It's kind of a hard sell if you have a manager that actually knows what's going on, convincing them like, yeah, I can't do this in PyTorch. I can't do this in any of these libraries that I've looked up. Scikit-learn doesn't have this functionality. XGBoost doesn't, but we need to solve this problem. and I can't do it with PyTorch, so I'm going to go build my own deep learning framework. You know, that's doing pure research in the realm of data science work where you're trying to solve not just your business problem, but you're trying to solve a fundamental problem. That's scary when unless you're staffed for that and you have an R&D team that has the rigor around how do we do R&D for tooling. Look where these sorts of frameworks came from. They came from skunkworks teams at Google, at Meta, at Microsoft. You have these core group of people that are doing pure research and building tooling that people at their company can use to solve very challenging problems. And then they're just nice and they open source it. But you need a specific group of people and support staff around them that are doing stuff like the things that nobody talks about, like at Google for development of the TensorFlow framework. That's not just that team of a bunch of CS research scientists that built that thing and they all did it on their own and then just open sourced it. It's like, no, you have software engineers helping build that and maintaining that. And you have test infrastructure engineers that are building, you know, other tooling that's used for doing CI for that, like Bazel, the entire build tool for that. That runs all of their test orchestration. There's an engineering team that owns that and supports that. You have people that are doing the deployment of that and doing integration testing of it and validation and doing bug bashes and stuff. There's a lot of people involved in that. So if your company doesn't have that support infrastructure and you're trying to solve a business problem with tooling, it's important to realize the difference between, like, what is our goal here? Are we trying to open source something to solve a nascent problem that nobody else has ever encountered before? Do we even have the ability to do that? Should we be going down that road? Or should we say, is there something else we can work on? Or maybe we should go and do a little bit more research and see if there's a different way of solving this.
Yeah, there was a related topic that we were discussing before recording that I think is super interesting and super relevant, and that is how does the ratio of scientists to engineering differ as a function of company size and as a function of your industry? So let's use OpenAI as an example. They're probably the most hyped company for per number of employees. And so I'd be curious, Ben, if you started OpenAI on day one, knowing their product line and knowing where they were, would you hire scientists? Would you hire engineers? And then what would be the inflection points where you start hiring more or less of one category?
I mean, my first hire would be a CTO who has done that before and is like highly skilled at doing that, and then talk with them every day.
Would
Uh,
you call a CTO a scientist or an engineer, or can they live in both worlds typically?
that's an engineer,
Got it.
100%. Um, Even if they did do R&D research in the past, you wouldn't want somebody who doesn't have engineering experience running an engineering organization.
Probably.
That would be scary. Doesn't work out well for anybody. So I would respond to the inflection point based on how fast we're getting to market and how far along R&D is. And that's something that you would adapt over time. So you would know when to make a change in hiring based on the market effect. Like, hey, if we're getting super popular and we're able to, you know, our service can handle query loads just fine, and everything is built and designed in a way that it's stable, reliable, things just work. We're able to be productive over time and maintain a high velocity. We maybe have enough engineers and good engineers at that. But if we have service stability issues and scalability problems and we're an actual real world company that has all of those things, it would be a blend of like, where do we actually need people, and what what skill sets are we looking for, and how much experience do we need from candidates in order to come in and do this.
So it sounds like the causal feature in this relationship is not company size, but it's almost infrastructure stability. If you have low infrastructure stability, you probably want more engineers. If not, you want more scientists? Or do you think that engineers can do some of the science almost and innovate in creating new products?
I mean, if I'm the one hiring all these people, I don't want them doing that because I've seen how that plays out in other industries. I've seen how it plays out in software industry as well. If I'm hiring an engineer to like make my product stable and reliable and build features that enhance the user experience or reduce the friction of using this product, I want them to do that. I want to find people that want to do that, are good at that, and want to learn how to get even better at that. I don't want to hire somebody who wants to do research, but they're getting paid and are being tasked on a sprint basis to make something better because they're going to get
Right.
really frustrated and quit, or they're going to develop a really toxic, you know, personality while at work and bring everybody else down. I would not be interested in having that person. If they want to go do research, you know, apply for that job at the company. And if you don't get accepted into that job, then go apply at another company for that job. Go find your piece. Go find the thing that you want to do. Somebody out there will have you to do it. But if you come in with that thought of like, oh, I want to go and innovate and invent and do all this cool stuff, and you take a job as a software engineer, you like that could happen. You could file some patents. You could invent something new that nobody's ever done before, but that's not an expectation of that role. Whereas if you're going as an R&D scientist somewhere, that's your core job. Go find like go find that undiscovered country. Find that blank part on the map and figure out what's there and plant a flag there.
Right. Yeah, I was actually giving a presentation at my alma mater at Penn to a sports research group, and it was cool to see a bunch of undergrads and grad students and sort of discuss what their hopes and dreams are in the data space. All of them generally want to work in sports research involving data, or are just selling their souls to finance companies, per usual. um, but it was really interesting to see this sort of divergence between the people that said, I really want to get into the data. I really want to solve real world problems. I don't want a clean data set. I want a messy data set. I want to explore and actually like deliver value. And then there are other people that sort of just want to play around and like try things and tinker. And I've always been the person that's very solution driven. Like if it ain't broke, don't fix it. But there's some people that can just spend hours and hours just saying, "Oh, I wonder what this does. I wonder what this does," and like curiosity really drive. And so it's been really cool to see this divergence sort of develop in myself, but also see it in a bunch of people that are about to enter industry, whether it's academics or the tech industry, and see how where they're starting at, what their perceived outcome is going to be. And I'm curious if it changes for some of them. I think it will.
I mean, it's got to. If you're entering the workforce, whether you want to go and do research or you want to go make product in any industry, this is applies to every industry I've worked in. I've worked in a number of them. You have to align your desires and what you want to do with what that job position is. Otherwise, you're either going to be very unhappy with what you're doing and you're going to end up quitting, or you're going to be really happy with what you're doing and your company is going to be very furious with what you're doing and you're going to be out of a job. So it's good to align your interests with what the job actually is, and make sure before signing on that piece of paper that that company, that hiring manager has been honest with you. And that's why it's important to ask your potential future peers, be like, what do you do in a daily, like day to day? What do you actually, what did you do today before we started talking? Like, what are you going to do after we start talking? It's like, stop talking. What are you doing next week? Should ask those questions. It always blew my mind doing interviews, and I've done thousands of them over my career now. The people that don't ask that question, I'm just like, that's the most important question to ask. And so many, like so few people actually ask it to understand, like, am I signing up for what I want to sign up for?
Yeah, no, I completely agree. But one nuance to that point is if you don't know what you like, just try stuff. Like it's not that
Right.
like you don't need the best job out of college. Like it'll sometimes take 3, 5, 10, 15, maybe even a career to find what you are truly passionate about. And so don't stress out if you don't know if it's a perfect fit, number 1, and number 2, even if you know it's not a perfect fit, there are often aspects of a job, if you keep an open mind, that are really awesome and that you can sort of specialize to. And sometimes even within that organization, there's lateral movement available where you can move into something that's more your speed. And so,
Mhm.
um, yeah, there's just like bias for action is really valuable. That's actually a Databricks culture value, bias for action. But it's true. Like if you're sort of just like over planning and are paralyzed by choice, it's typically really problematic.
Yes.
So Ben, I had a one final closing topic, which is I think it's really important. And after seeing many different organizations and many different data scientists, data engineers, and just data professionals, I think it's really important to be able to merge the skill sets of scientists and engineer and sort of not necessarily do both perfectly, but borrow from each of the core designs of and like the core tenets of these two professions. But before we get into that, you mentioned before we started recording that sometimes moving from engineering to science and science to engineering is not a smooth transition. And we talked about science to engineering, but what are your thoughts for engineering to science? Why is that sometimes challenging?
I mean, not just challenging, but in my experience of seeing that happen in a couple of different industries, it never works out because the mindset of engineering is optimization and taking, not taking shortcuts, but finding the minimum amount of work to do in order to solve a problem. It's all about efficiency, particularly about time. And that time component bleeds into a lot of different decisions or outcomes that we can talk about. It's like, hey, I built this simple implementation of this thing so that 6 months from now, I can understand how that works and change it easily if I need to. So maintainability. Or you're building, hey, I built this in the simplest way possible so that when we have to migrate away from this in the future, which we probably will have to do, I don't have to sink weeks of time in redoing all of this from scratch because it's very easy to change this. So that mindset is introducing a bias to your own thought processes that is not 100% conducive to how scientists approach problems. And everybody that I've seen that's done that, it's gone from like that engineering mindset into R&D. Uh, if they don't consciously try to fight against that, the habits that they've built, if they become a successful engineer, it's really hard for them to do that mental shift to say, "Hey, I don't really have those guardrails anymore. I now need to see what's possible and think more creatively, but also applying a much more structured and rigid approach to what it is that I'm testing out. You need to
Yep.
collect a lot more evidence. It's not the LGTM result from a unit test passing on code being like, yep, cool, good. The research side of that might be, I need to do stress testing of this, and I need to write these very complex integration tests and like load testing, and I need to really understand what the implications are of this design decision that I've made. If we're talking about software, if you're talking about physical science, in like you're making a product to put on into market, you're trying a bunch of stuff, but then you're collecting. To give you an example, those R&D teams making those LEDs, they would do their tests in a given morning. They would run all of their tests in the morning. The entire latter half of the day, they're in the metrology department, like slicing up wafers, doing atomic force microscope measurements. They're doing SEMs, TEMs. They're running this thing, this set of wafers that they ran, and trying to gather as much data as they can off of this experiment so that they understand what actually happened. They're controlling processes in special ways. They're, you know, doing specific things in order to answer the question that they've posed. Whereas on the engineering side, when we're making product, we would select one wafer out of the run of say 10 of them and send that out for a thickness measurement with non-destructive testing. It'd shine a laser at an angle at the surface of the wafer, and that tells you the thickness of, you know, the different layers that you just
Oh, that's
grew.
cool.
And
Interesting.
yeah, photoluminescent testing. So you would also shine a laser of a particular energy or light up certain aspects of the wafer to get the LED to light up, and then you would measure the wavelength and the intensity and measure the electrical characteristics of it. But you're collecting the data you need to do process control engineering. Just like, hey, am I within the bounds of acceptability tolerances of the product I just made? Am I making what I think I'm making?
Right.
And that's as far as the scientific aspect of it goes. That's now engineering process monitoring. And you are looking at data, but it's quick and dirty and fast. And you're like, yep, thickness is good on all the layers. My forward bias voltage is good. My leakage current's good. Light intensity is awesome. Okay, I have a winning recipe. I'm going to do that one again with some slight tweaks. Whereas
Right.
scientists are completely different, approach to that.
Yeah. So let's close out with some tips for engineers from a science perspective, for scientists from an engineer perspective, and then if you got some tips in common around this realm, let's do that as well. But I'll kick it off for engineers from a science perspective, which is stay in the problem space more. Typically, engineers rush to build a solution, and if you know how to build it, freaking go ahead. That's like, don't spend time planning if you already know the solution. But often spending even like an extra hour or even sleeping on it overnight, you'll come up with a much simpler and a much more robust and a much more effective and creative solution. So prototype, but don't jump to building a final solution and instead explore the space.
Could not agree more.
Cool. So you got one for either direction?
Yeah, for people in the engineering space, like, do your research. And this is a message to my younger self and my current self and my future self. Like, do not forget to figure out if this is a solved problem. You're looking at something that you don't understand in code. You're like, man, I need to do this thing where I take the data and I change it to this other type, and then I have to make sure I can serialize that and then deserialize that and send it over the wire. Figure out if that's been solved. And if it's part of like the core language, please use that. If it like test things out, and the way that I do it now is I always test sort of the happy path first. Like, what's the easiest thing for me to do to solve this? And then test it and say, does this solve it? If so, awesome, move on. Next problem. But if it's, yeah, this doesn't quite do what I need it to do, now when you get to that point, somebody without very much experience would say, "Oh, time to reinvent the wheel. I got to go and build something for this." uh, that's dangerous. The best thing to do is there something else that exists that'll solve this that's just slightly more complicated than what I'm doing right now? If so, test that. If that works, use it. And eventually you get to a point if you're going through that iteration cycle and saying, okay, I'm going to test the next thing, see if that works. You can't exhaust all the options. And at that point, that's not go off and build a new thing that does this thing. That's the time to go talk to some friends. Get
Right.
a peer review, ask people, be like, hey, you ever solved anything like this? Do you know if this is, am I thinking of this right or am I being dumb? And most of the time, it's you're being dumb. Um, but sometimes you ask a bunch of people and they're like, yeah, man, I don't think that anybody's solved that before because nobody's ever had to solve that. Or if they have, they're not sharing it with the rest of the world. Uh, then it's time to go and ask people like, should we build this? Is this worth our time? Let's go scope what it would take to build this.
Right.
And sometimes that scope is it's 2 days of work. It's going to be a pain in the ass if we ever have to change this thing, but let's write it in such a way that we understand it and it's easy to maintain. Or it's this is going to take us 6 months to build, and it like what is the end goal here? Is this to solve this one problem that somebody asked for that makes the company $100,000 a month at max? Is this worth 6 months of our time solving this problem? Usually the answer is no. Move on to something else.
Yeah. Yeah, the amount of times that I've invented something and then a week later realized that there's a million open source solutions, it's just it's just mind-blowing. And I was so proud of my invention too. But at this
Yep.
point I sort of expect it to happen anytime I write any code. So, on the flip side, for scientists from an engineering perspective, I think engineers are really, really good at knowing their tool set. So if you look at a lot of software engineers, if you look at their VS Code setup, their Vi key bindings, their vimrc files, like all these things that help them uh, produce in an efficient and scalable manner, it really is valuable. And if you're a scientist, a big part of creation is creative iteration. And if tools are blocking your mind from sort of wandering, it's really bad. And so just learn your tools. Like spend a weekend, play around with it, or spend a week on your like on job time. It will pay dividends down the road.
Yeah, and learn the languages that you're writing your experiments in.
Right.
Like if you're writing shit code, like what are the results of your experiment? Is it a byproduct of your idea is good or bad, or is it your
Exactly.
implementation is good or bad? So yeah, if you're in the realm of software engineering, you have to like learn software engineering if you're doing research. And most good people are like they're pretty good developers. In the physical sciences, my experience was the embedding was the answer there. So it's there's not enough time in the human life span to become like postdoc level experience with material science and understanding all of that stuff, which it's a mountain of knowledge and understanding concepts and theory. Getting those people to be really good at operating the tools that they were using to grow those structures, they could write recipes, definitely. It's not that challenging. Like they're smart people. But do you want them changing out valves on the machine and like soldering pipes together? Probably not. Like, the engineers are the ones that know how to do that stuff. So they would be embedded in that team to be like, hey,
Right.
you're here as sort of support staff to help them out if they get stuck. And that works really well. Same kind of work with data science too. Some of the most effective data science teams that I saw pump out the most reliable and sustainable projects were those that it was like 4 data scientists and 2 software engineers. They're all working together on this project, and they produce something that works in prod. It's like, great, and the model's good, and there's some mechanism to retrain it, and yeah. But you get a bunch of people who don't know how to do all of those different things, now having to do all those different things, it's probably not gonna be that great.
Yeah. Yeah, heard. All right, so I know we're coming up on time, so I will quickly wrap. Today we talked about science versus engineering, and while they share a lot of skill sets, they are typically quite different in terms of job description and what makes a good person good at each of these. So in engineering, typically you're looking for solving an optimization problem. You're looking at how to best implement something in the least amount of time possible. And you must master both tooling and theory to resolve this, but typically you're less driven by curiosity and exploration. Science, on the other hand, is a lot more about what is the next big thing, and you let creativity and curiosity drive. And it's important to be able to build prototypes and scope, but you're more sort of an undirected person. And then one thing that's common for both, though, is building maps, whether you're building a condensed map of vehicle parts or you're building a large map of the entire continental US. Both of these are essential skills. And the underlying essential skill is map building. So I think that's about it. Anything else, Ben?
No, sounds good.
Cool. All right. Until next time, it's been Michael Burke and my co host.
Ben Wilson,
Have a good day, everyone.
we'll catch you next time.